wonder why he's so negative. That's not my joke. But I'll happily repeat it. Yeah. John works as part of OpenSolaris engineering. I think that's approximately correct.
Yeah, I work in packaging and user-land stuff.
Yeah. So if you want to talk Perl in OpenSolaris, talk to him. Especially Perl 5.10.
Next week.
I'll believe it when I see the RTI. Okay. So he's going to talk about drivers.
I'll send it right to you.
He gave me an RTI yesterday, just before I was about to leave the office.
Do it at the pub. Do it at the pub.
Yeah.
Buy one at the pub.
John is going to talk about drivers and device driver and driver kernel interface frameworks that we have in OpenSolaris. Take it away, John.
Hello. So, thank you. So as James introduced, I'm John Sonnenschein, and I work at Sun in OpenSolaris engineering. So drivers in the OpenSolaris operating system, we have a few different frameworks that you would use for drivers. A few of them are kind of the same. One of them, specifically the file system driver framework, is completely different and weird. And so I'm going to just do a quick run through of all of them. And this talk isn't really designed for Garrett, who's written, I don't know, how many drivers have you written? Most of them. It's kind of a more basic talk for people who want to get into writing drivers. So without delay, assuming this decides to ever work. Oh, there we go. So the basics of drivers. In Solaris, every device lives on a device tree, where each node is a device, and it lives on a tree. So you have nexus nodes and you have tree and leaf nodes. And the tree shows its physical location. On the slides, I have a /devices. That's all of your devices. And it can have a child /devices/PCI, and that's on this machine. There's a PCI bus, and you can dig further down. So on the PCI bus, there's an HBA. It'll be /devices/PCI/whatever, and so on and so forth. And if you want a listing of your device tree, you would use the PRTconf utility, and it's documented in manual page 1M. And yeah, you can get your entire list of device tree, your entire device tree with that. Some of the files that are important to drivers are /etc driver aliases, path to inst, name to major, minor perms, the /kernel drv driver.conf file. That's your configuration for the driver, and /kernel/drv. I put AMD64 there. It's just your ISO directory. So just plain is for your 32-bit, AMD64, Sun 4, or whatever. And some of the utilities you'd use for playing with devices is add drive, remove drive, update drive, mod info, mod load, mod unload, and devfs admin. So some of the different device driver classes that we have are character and block devices. Those are two closely related ones. We also have different frameworks for net drivers, for USB drivers, for SCSI target and HBA drivers. Those are both part of the SCSI framework, and for file system drivers. So for character and block devices, you have to include a number of entry points and data structures. So the init entry points, init info and fini are the ones you need to load as a module at all. Attach, detach, and get info are to be useful as a module at all.
Also, by the way, all 6 of those are required for every driver, just in some frameworks.
Yeah.
Fill them in for you.
Yeah. Well, no, I meant more that you can load a module with just init info and fini, but to do anything, you need all of them. And there are a few standard functions that you can use. You don't have to define them, but to do any useful work, you do. Open, close, read and write, etc., for reading and writing to the devices and so on. And a list of mandatory headers, mod control, common error, DDI, SunDDI. Some of the driver support functions are if we want to do memory allocation and mutexes, basically all of the stuff that you would need a driver to do: allocate memory, hold mutexes, do DMA, et cetera, et cetera. For memory, you would use kmem alloc and kmem free. You can also create caches, destroy alloc, and create the caches. And if your driver is going to use interrupts, mutex init needs to be the last argument. The last argument to mutex init needs to be the interrupt priority, which you would use, or which you would get from DDI enter get prio. What's next? Register support, DDI register map setup and get and put. You would use those for registers and memory mapped I/O. They're all pretty well documented. DMA, you have DDI DMA adders is a data structure. You have your DMA alloc free handle, adder buff bind handle, unbind handle, etc. If you wanted to do DMA, the first thing that you would do is you would allocate and initialize a DDI DMA adder struct, which describes a device and DMA engine specific attributes. This is a global static initialization within the driver. You can allocate a DMA handle with alloc handle, either in attach or just prior to programming the device to do specific DMA transfer. Then you would bind an address to the handler with DMA adder bind handle or buff bind handle if you wanted it buffered. These routines they return a DMA cookie or cookies that contain the addresses and size used to program the device. And then you would program the device to do DMA, and that would be specific to your actual hardware device. On completion, you need to sync it. You may need to sync it with a call to DMA sync. When you're finished with the I/O, you can unbind the handle to free up the DMA resources. And when you're finished with the handle, or in detach for detaching the driver, use free handle. So interrupt handling. We have several different kinds of interrupts. You have legacy interrupts. Those are those would be like your old interrupt lines. And we have MSI and MSIX, which are pretty closely related, and software interrupts, which are useful if you are a high-level interrupt and you need to bring your you need to bring your priority down so you don't hang things. MSI interrupts use in-band PCI memory space to raise the interrupt instead of the conventional like interrupt X pin. So yeah, when you need to use MSI, you'd set up your registers. It would be a write address register and a data register. Where are we? So legacy interrupts. What you need to do to register a legacy interrupt is use DDI enter get supported types to determine which types of interrupts are supported. Get and enters to determine the number of supported interrupt types. And use kmem zalloc to allocate the memory for the DDI interrupt handles. And for each interrupt type that you allocate, take the following steps. To use DDI enter get prior to get the priority of the interrupt. And if you need to set a new priority, use DDI enter set prior. Use enter mutex to initialize a lock. Add a handler to register the handler for the interrupt. Enable the interrupt with DDI enter enable. And then you are handling interrupts. When you need to free it, just disable with enter disable, remove the handler, mutex destroy, and then free and kmem free.
What about the iBlock cookie?
What about it?
Cookie goes back to this is the new
I
style.
want him to answer.
Sorry.
Why?
It's a legacy concept.
This is the new DDI.
Oh, too many slides. Yeah. The MSI interrupts. I've highlighted the inter-alloc because that's the main divergent point. The steps are relatively the same for registering an MSI interrupt. Get supported types, get in enters, alloc, get the priority, set it if you need to, enter mutex, and then add the handler. You can also enable with MSI a block of interrupts with DDI inter block enable. Or you can enable them each individual with DDI inter enable. So an interrupt handler, what does it do? It can triage and reject the interrupt. So if your device isn't interrupting, you can just reject it. So you would look at it, and see whether the device issued the interrupt at all. And if it didn't, then you need to return DDI inter unclaimed, and that enables the implementation of device polling. So the interrupt can go to the next handler. Once you do claim the interrupt, you need to inform the device that you are claiming it, and possibly prevent further interrupts if you need to mask them. Do any I/O, and return DDI inter claimed. MSI interrupts always need to be claimed. What are we next? High-level interrupts. Oh yeah, if you are at the level of the scheduler or above, which you would find out with DDI inter get prio, then your interrupt level doesn't let the scheduler run. So your high-level interrupt handlers can't be preempted by the scheduler. So what you want to do if you don't need to sit there and preempt the scheduler is lower your interrupt or fire a software interrupt. Yeah, you need to be careful with high-level mutexes. For that reason, you can cause deadlocks. And yeah, you can lower your priority by calling a software interrupt. Network device drivers. So a network device drivers can be used with a different framework. They are streams drivers generally. They communicate with the DLPI via with the protocol stacks. And there is a framework which will make this a lot easier. It's called the GLD, the generic LAN driver. It's multi-threaded, clonable, loadable kernel module. And it implements most of your streams and DLPI functions. It really makes network drivers a lot easier. So you do need to compile it with the GLD header, obviously. Link it with the MISC GLD to register the driver dependency. And I put up the example of your QInit structure. So the GLD implements open, get info, and close for you. Put and serve are both required by streams. You still need to implement init, info, fini, attach, detach, like all the modules. And then the GLD offers you a whole bunch of functions and callbacks that you can use. So reset, start, stop, set your MAC address, set multicast, set promiscuous, send, inter, get stats, ioctl, and so on. Another driver class we have is the USB drivers. They can be block, char, or streams. The difference is in the USB-A framework, which abstracts devices, and you would call that instead of the driver hardware. And it kind of works like pipes. Device IDs can be compatible. They don't necessarily need to be fixed. And the devices can have multiple interfaces. I put up here a link to a USB skeleton driver that's on Big Admin. And yeah, I don't know, it's a good place to read about the USB drivers. Yeah, like I was saying, USB passes requests through pipes. So you have control, bulk pipes, data, interrupt, and isochronous. And every device has a default pipe retrieved from USB get dev data. These functions, USB pipe open, close, get dev data, and lookup, you use them to create, close, and get endpoints. Requests can be initialized and freezed with USB alloc and free, control bulk, enter, isoc request. These are all, because there's a whole lot of functions, instead of writing them out individually, I've just put a little thing right here. And requests can be transferred with USB pipe, whatever transfer weight. Pipes can be cleaned after errors with pipe reset. Hot plugging, you have a register hot plug callback function. I don't know why that's 3FF, but power management, you have power and USB create PM components, which you would use and attach. Busy component and raise power, idle component, USB handle, remote wake up, etc. Another class of drivers is SCSI target drivers. They can be character or block drivers. The SCA framework separates the SCSI command from the transport in HBA. And yeah, you would just use SCSI transport. You do need to register the dependency, like in the GLD with MISC SCSI. Allocate and initialize SCSI devices before probe or attach, for example, in your init function. And you'd implement probe to auto-configure, in which function you would call SCSI probe and unprobe. Attach and detach must call the SCSI probe and SCSI unprobe. And the SCSI drivers pass commands through the SCSI packet structures, which you can read in the manual page. And those are what you pass to SCSI transport. They contain a callback, which the HBA calls once it's done with everything. And the HBA drivers, which are still connected to the SCSA framework, but on the other end of it, they're responsible for managing the hardware, accepting the SCSI commands from the target driver, transporting the commands to the device, performing the data transfers by command, collecting status, auto request sense, which you don't have to do, and informing the target driver of command completion through that callback that I mentioned earlier. And HBA drivers are Nexus drivers, so there's more of the DDI that you do need to implement for them. Your key data structures in the HBA drivers are HBA trans, SCSI address, and SCSI devices. Your functions are SCSI HBA init, fini, attach, setup, detach, transaction alloc, free, packet alloc and free, probe, lookup, transaction target, that list, transaction DMA free, start, abort, reset, etc. And each command is in its own SCSI data structure. And now on to file system drivers, which are quite different from the rest of them. And there is no interface stability in them, so a file system driver won't necessarily work across Solaris versions. They're also not well documented at all. Sorry?
They're not documented.
Yeah. Yeah, they're documented with code and slideshows. Anecdotes. So your files and directories that you use is /kernel fs name and the 64-bit version of it. User kernel fs name, user lib fs name, and the fs name here is like PCFS or ZFS or myFS or whatever you like. So the /kernel subdirectories are kernel. They actually contain the kernel file system drivers themselves. Like any kernel drivers, they're an architecture-specific binary. The user lib and etc. stuff are in for your file system specific utilities. So, for example, like makefs, PCFS, and the makefs and fsuc and stuff like that call these directly. So unlike your character and block devices, you don't provide any static function tables, so you don't need CBOps or DevOps. You do need to create the mount ops table, and those will be your options like, for example, mount async or whatever. Where are we? The fsinit function initializes everything else. Pardon me. The VFW has myFSInit in it, which would be your initialization routine, mount options I mentioned earlier. In your mod linkage function, modrev1 is a mandatory field. You can't change it to anything else. So your mount option table, this is what the table actually looks like. You have the mount option name, so async, mount option cancel, which is a list of things that your option cancels. So if you are mounting read-write, for instance, it would cancel read-only. The argument string, where are we? The flags for the mount option, and the file system specific data in it. The VFS framework passes and validates the set of parses and validates a set of generic options, which are, again, documented in the code in user source UTS common fs vfs.c. You can get some more out of sys/mount.h. So there's two sort of sets of interfaces for file system drivers. One of them affects one instance. So this would be your one file system, your file system sitting on a partition. And these are your VFS operations, as mount, unmount, sync, etc. And the other ones are operations on nodes. And nodes are your files, directories, pipes, devices, what have you. And these are all your vnode ops. And so the userland functions that they correspond to are open, close, read, etc. VFS lets you instantiate and discard an instance, so that's your mount and unmount. Vnodes are the backends to the file interfaces, mmap,